Hi everyone. Today I want to go through this problem from an Indian Math Olympiad, 1999, problem 2. And so another math YouTuber named Let's Think Critically did this problem 2 weeks ago, and I'll put his video in the description. And he shows two ways to solve this problem, and I came up with another solution. Now, admittedly, it's not a very good solution, and it uses, I use some calculus, just a small amount, um, but I think it warrants maybe a video on it. Probably not something you would want to do on an Olympiad. It's definitely not a very elegant solution. But anyway, let's get into it. So we want to find integers x and y, which are non-negative, so they're greater than or equal to 0, such that this following equation holds. X times y minus 7, all squared is x squared plus y squared. And if you look at this equation, right, you might be tempted to think Pythagorean triples, right, because you have something squared equals something squared plus something squared. And indeed, one of these solutions that Let's Think Critically does involves this, right? It involves Pythagorean triples. But I kind of have I had a different solution. So basically my solution uses kind of a bit of casework, right? So the first thing we can consider is, what if x is equal to y? Well, in that case, you get the equation x squared minus 7 squared equals 2x squared. Right? Just putting in, substituting y equals x. And so what we notice is that this is a quadratic equation in x squared, right? So maybe I'll call this u. So if I call u equal to x squared, then this is u squared minus 14u plus 49 equals 2u. And if you simplify this, what you get is you can complete the square and you get this equation. U minus 8 squared is 15. And this does not have any integer solutions, obviously, because you would get essentially x squared is 8 plus or minus the square root of 15. And obviously there's no integers that square to a non-integer number, which this is not an integer, right? So the case of x equals y has no solutions. So another note that we can make about this equation is that the equation is symmetric in x and y, right? In other words, if you were to swap x and y, then the equation is still true, because essentially if you swap x and y here, x times y is the same thing as y times x. And if you swap x and y here, well, you get basically commutativity of addition there, right? So commutativity of multiplication and addition imply that this equation is symmetric in x and y. And so since there are no solutions for x equal to y, we can impose the condition. So this WLOG means without loss of generality, we can say x is less than y. Because if we find all the solutions with x is less than y, then you just flip those solutions. You flip x and y in those solutions to get the other solutions. So we're going to assume that x is less than y. Okay. Now let's do some other cases. So basically we're going to do casework on x now. So the first case is if x is equal to 0. And if x is equal to 0 and you put that into the equation, what you get is 49 equals y squared, right? So if you just put in x equal to 0 in this equation, right, x times y is going to be 0, so you get 7 squared, or negative 7 squared is 49, is 0 plus y squared, so you get y squared is 49, y is, y is going to be positive, so you just get y equals 7. So this gives you a solution, so we have a solution of 0, comma 7. And note also that since the equation is symmetric, we also get a solution of 7 and 0. So far we have 2 solutions. Okay. And I'm just going to go through a few more cases, and we'll see why I'm going to do these cases in a bit. So next we go on to x equals 1. So if we just put x equals 1 into this equation, right, we get this. And this equation, right, so if we expand out here, notice it has a y squared and a y squared on both sides. So this actually becomes a linear equation, and what you end up getting is 14y equals 48. And 48 is not divisible by 14, so there's no integer solutions. So no solution here. Our last our last like case for what x is equal to exactly is going to be x is equal to 2. Okay, so for x equal to 2, again we just stick this into the equation, right? Expand and group everything up. And so what you get is this equation. Now, we make the observation here that 3y squared, if y is an integer, right? So we want y to be an integer. So if y is an integer, then 3y squared is divisible by 3. And 45 is divisible by 3. Right? So that means since 3y squared plus 45 equals 28y, and 28 is not divisible by 3, then that means y itself has to be divisible by 3. So I'm running a little low on space here, so let me just copy that equation down again. So 3y squared minus 28y plus 45, 0. And so what we have is that 3 divides y, if y is an integer solution to this. And so we can write y as essentially 3 times, let's say 3 times z. Actually, let me use w first, because we're going to have another z. And so if you put that in here, well, you get 27 w squared minus 28 times 3 w plus 45 equals 0. And we can divide out by a 3. So if we divide by a 3, get 9w squared minus 28w plus 15 equals 0. And then we have the same thing, right? Basically, 28w is going to equal 9w squared plus 15, which is a multiple of 3. So this implies 3 divides w. And so we can write w as a multiple of 3. And so putting that in here, we're going to have, and after dividing by another 3, so if we divide by 3, what we're going to have is 27z squared minus 28z plus 5 equals 0. Okay. Now, uh, now we make an observation that what we can write this as is we can write this as 27z minus 1 times z minus 1 plus 4. Okay, so essentially if you write this as a 1 plus 4, then, this whole thing factors. Now, what is z? Well, y equals 3w and w equals 3z. So these things put together means y is 9z. And remember that y was greater than x, right? That's what we assumed. And in our current case, x equals 2. So y is greater than 2, and it's a multiple of 9, which means that z is, this inequality means z is at least 1. Right? It can't be, basically it can't be 0, because then you would have 0 is greater than 2, which is not true. So z is greater than or equal to 1, and what that means here is that this is greater than or equal to 0. So we have something greater than or equal to 0 plus 4 equals 0, and so this is not true. So there's no solution here. So now we just have the case of x is greater than 2. Okay. So what we want to do now is take our equation xy minus 7 squared equals x squared plus y squared, and write this as a quadratic in terms of y. So basically, if you expand all this, you'll get an x squared y squared term, an xy term, a 49. You have an x squared and a y squared here. So basically, you just want to group these things together in terms of y. And so what you get is this. I'll put parentheses around this. Get this is equal to 0. And so this is basically a, and I can even put parentheses. Yeah, I'll leave it like that. But I've written this as a quadratic in terms of y. And so what we're going to do is we're going to use the quadratic formula. So with the quadratic formula, we know that we can basically write the solution for y in terms of x. And so that's going to give us the following. 196 x squared minus 4 all over 2 times x squared minus 1. Okay. And so let's look at this this discriminant for a second. So we have this minus 4 stuff. So basically we have, we have 19. Well, first we can notice that this is 196 is 4 times 49. So we can take out a 4 from everything, and that's going to be a 2 on the outside. So we're actually going to have a 2 that cancels out with everything. So I'm going to do that real quick. And so if we look at our discriminant, we have 49x squared minus, but I'm going to distribute the minus into this 49 minus x squared. So it's going to be plus x squared minus 1 times x squared minus 49. And this is going to give us x to the 4th minus x squared plus 49. Okay. Because you get a minus 50x squared here. And so 49 minus 50 is -1. And so that's what you get here. So this is our discriminant. So let me just rewrite everything here. Okay. And now what we're going to do is we're going to use the fact that this is greater than x, right? Because this is equal to y, and we know that y is greater than x, right? That's what we assumed. Now, x is greater than 2, so x squared minus 1 is surely positive, so we can multiply by x squared minus 1 on both sides, and then subtract, so this is going to be x cubed minus x, and then subtract 7x, uh, and so then what we get is plus or minus the square root of this determinant has to be greater than x cubed minus 8x. Now, remember that in our case, we have x is greater than 2. So the reason why I chose this case to stop picking basically specific values of x is that when x is greater than 2, x cubed, so I'll write this, maybe I'll write it here, x is greater than 2 implies that x cubed minus 8x is greater than 0. And basically the way you can see this is, well, this factors as x minus, or x times x minus 2 times x plus 2. So this has to be greater than 0 because you basically have something positive. If you subtract 2, it's still positive, something positive. So you're multiplying positive numbers, it has to be positive. And so if x cubed minus 8x is positive, then it can't be less than a negative number. So that rules out the negative sign from the quadratic formula, and so we know we only have the plus sign to worry about. So let's go on to the next page and basically rewrite what we have now. So we have only the plus sign. We have the square root of our discriminant is greater than x cubed minus 8x. And this happens to be greater than 0. But we won't need that, I don't think. Okay. And we know x is greater than 2, right? So now we square both sides because these are both, well, actually, yeah. So we do want that this is greater than 0. So we have two positive numbers, two positive real numbers, and so we can square both sides and still get a true inequality. So we square both sides. So on this side, we get this. Just get the inside of the radical. On this side, we get x to the 6th minus 16x to the 4th plus 64x squared. And if you put everything on the right-hand side, what you get is this. Okay. And so this is an inequality in this 6th-degree polynomial. However, notice that this isn't this is a very special 6th-degree polynomial in that it's actually a cubic in x squared, right? So this is a cubic in x squared. So if you let u equal x squared, then we have a cubic. Now, the fact that this cubic is less than 0 is very important. Why is it important? Well, this cubic has a positive leading coefficient, which means if you plot it, right, an arbitrary cubic is going to look something like this, with a positive leading coefficient. And a cubic will go to positive infinity as its as its independent variable goes to positive infinity. So basically, as x gets large, right, then u is going to get large, and therefore this stuff will have to become positive, right? And so that puts a restriction on our values of x. Basically, our values of x cannot be too big, right? And so now we just need to find what is that upper bound. What can x not be equal to? Now, remember that x is an integer, and we're currently assuming that x is greater than 2. So the first thing would be basically to check some values, right? Let's say check x equals to 3. So what happens if x is 3? Well, we get 0, so we get 729 minus 17 times 81 plus 65 times 9 minus 49. And if you work that all out, then what you get is negative 112. And so certainly negative 112 is less than 0. So x equals 3 is fine. It passes this inequality, basically. And we can also look at, well, what about, say, x equal to 4? What happens with x equal to 4? So we have 0 is going to be greater than. So I think 4 to the 6 is this, right? So 2 to the 12 minus 17 times 256 plus 65 times 16 minus 49. And if you work all that out, then you get 735. And so this is false. So the inequality fails for x equals 4. And now what we want to show is that it's going to fail for all x greater than or equal to 4. So we want to show that basically, so we want to prove that for x greater than, basically x greater than 3, then the inequality is false. So I guess I should specify integer x greater than 3, the inequality is false. So how do we show that? Well, again, looking at the sort of having this graph of an arbitrary cubic in mind, we basically need to know, well, at 3, or, I guess if we want to think about the cubic, then we should think u equals 9, right? So at u equals 9, let's say that's over here, we have a negative number. And at u equals 16, we have a positive number. So basically, we want to show that that the function is increasing and will stay increasing basically at x equals 9, right? So what we're going to show is that at x equals 9, the function is already increasing for its final time. So notice, like, a cubic will increase twice, right? So it increases from negative infinity to some point, and then it increases from some point to positive infinity. And so we want to show we're on the right of that second, what we call a critical point. And so this is where we are, my solution uses calculus, so maybe not quite equipped for a high school Olympiad, but so usually people who are doing Olympiads may know calculus. And so the reason I've changed this into a cubic is so that it's easier to take the derivative and find when the derivative is equal to 0. So we have, sorry, I instinctively wrote that there. So let me copy down this cubic. So we want to find when this function is increasing. So we take a derivative, right? So d du is 3u squared minus 34u plus 65. And so we want to find basically if we find the solutions to this, this is a quadratic, it's going to have at most 2 solutions. And if we show that what we want to show is that 9, this function is basically increasing, or 9 is on the right-hand side of its roots, basically. And so the solutions to this are 34 plus or minus, and we only want the plus, right? We want the bigger roots. We want the plus 34 squared minus 12 times 65 all over 6. And so we claim that this is less than 9. And it's pretty easy to basically just check this, but straightforward. So you multiply it by 6, so you get 54, and then subtract 34. So you subtract 34, and you get this. Okay, and then you square both sides. On the right-hand side, you get 400, and on the left-hand side, you have 34 squared minus 12 times 65, which happens to be 376. So this inequality is true, meaning that 9 is on the right-hand side, right? So 9 is over here, which means that this function is, our cubic, right, is going to be increasing for u greater than 9, which corresponds to the 6th-degree polynomial increasing for x greater than 3. And so since we know it's positive at x greater than 4, then it will always be positive for basically for all integers x greater than or equal to 4. So to recap everything we just did, so what's our recap? Well, our case, we were working on the case x greater than 2, right? And we showed via the quadratic equation for y that x less than y implies, essentially implies x is 3. Right? Since there's no solutions for 4 or above, and x is greater than 2, so x equals 3 is the only possibility if we have any solutions. And so what that means is that we can just put x equals 3 into back into our equation. And in fact, we might as well just put it into the quadratic formula. So remember, we had y is 7x plus or minus the square root of x to the 4th minus x squared plus 49 all over x squared minus 1. And you just stick in x equals 3, so you get 21 plus or minus the square root. You get 81 minus 9 plus 49. This happens to all equal 121. So we have square root of 121, which is 11. On the bottom we have an 8, so we get 21 plus or minus 11 over 8. And we notice that the minus gives us a non-integer solution, so you get 10 over 8. But the plus gives you an integer solution of 4. And so that means that that we get a solution of 3 and 4. And by the symmetry of the equation, we also have the solution 4 and 3. And so we've exhausted all of our cases, right? So we started with the case x equals y. We showed there's no solutions there. And that means by symmetry, we can just consider x less than y. We did x equals 0, right? So since x and y are non-negative integers, x is going to be greater than or equal to 0. So we can start at 0. We showed that there's a solution for x equals 0, and we can swap x and y to get another solution. We showed x equals 1 and 2 have no solutions, right? So for x equals 1, we just had the only possible value of y was not an integer. And for x equals 2, the integer solutions, we use this divisibility by 3 trick to show that there's no solution there. And then for x greater than 2, we were able to show that the only possible x value such that x is less than y is x equals 3. And that gave us, if we plug x equals 3 into the equation, we get the only integer solution is y equals 4. And swapping x and y gives 4 and 3. So those are all of our solutions because we've exhausted all possible cases, and so we are done. So I hope you enjoyed this video. I know it was a bit long, Let's Think Critically's video covered 2 solutions in like half the time, but this was a very messy solution, and maybe it will kind of show you that sometimes on Olympiad problems you can crack them by a sort of brute force, although usually there's better ways to do it. So yeah, I hope you enjoyed the video. Please watch Let's Think Critically's video as well. It's a very good video, and thank you for watching.